All right, guys. So today we will be solving problem 45 from section 6 of chapter 6 of Physics Principles with Applications. This problem asks us about the work done against gravity and the tangential force applied on a set of pedals on a bicycle. So I'm going to start by setting up the problem that was given, and the way I'm going to do that is draw the hill as a triangle, right? So let me go ahead and draw this hill right here. We've got a theta, which is the incline angle that they've given us. We've got, I'm going to mark this as H2 and mark this as H1. And we know that H2 minus H1 is equal to 125. So I'm going to go ahead and write down some of the values that they have given us, that the problem has given us to start out, which will help us out as we move along to solve parts A and B. So we know that the change in height is 125 meters. We know that the pedals turn in a circle that has a diameter of 36 centimeters, which is equal to 0.36 meters. And I'm changing it all to meters to keep it easy as we move along. We know that the mass of the cyclist and the bicycle is equal to 75 kilograms. And I'm going to mark that down as M. And a couple other things. We know that theta is equal to 7.5 degrees. And later on, we know that the distance traveled in one revolution of the pedals on the bicycle, so I'm going to mark that as x rev, is equal to 5.1 meters. So let's go ahead and start part A of this problem. So we know that part A is looking for the work done against gravity, and I'm going to denote that as W sub G. And we know that the work done against gravity is equal to the change in potential energy, which I'm going to mark as delta PE. Now we know that the change in potential energy is equal to the potential energy at height 2, right? So I'm going to mark that as P sub H2 minus P sub H1, right? So the formula for potential energy in this case is going to be mass times the acceleration due to gravity multiplied by the height at that location. Now, we know that this, if we go ahead and just transfer this formula down right here, right, we're going to get mgh2 minus mgh1. So we can go ahead and factor out the mg's. And now you'll notice that we know all of these values. We know what m is equal to, we know what g is equal to, and we know that h2 minus h1 was given in the problem as well. So I'm going to go ahead and say that once we substitute 75 kilograms for mass, and we know that once we substitute that, and I'm going to go ahead and actually just write this down all together. So now we know that the work done against gravity is equal to mg times the change in height, right? And we know that this is equal to 75 kilograms for the mass and 9.8 meters per second squared, which is the acceleration due to gravity, and we know that the change in height is 125 meters. Now, if we multiply all of these things out, then what we should get is 91,875 joules, right? Now, because of the sig figs that were given, so we were only given 3 sig figs in this value right here, which is the max, I'm going to go ahead and say that the work done to gravity is equal to 9.19 times 10 to the 4th joules. Okay, now let's move on to part B. For part B, we need to calculate the tangential force that are applied on the pedals. All right, so for part B, we know that the work done on the pedals, which I'm going to denote as work or W sub P, is equal to the change in potential energy during one revolution, which I'm going to mark as PE sub rev, right? Now, let's go back. Now, first things first, let's go back and look at what's going on here. So let's say that in one revolution, the bike travels this distance right here. Then, if we were to draw a little dotted line on our diagram, I'm going to keep a little h, I'm going to call this h prime right here. So that is the distance traveled during one revolution, right? And that's going to be used for our potential energy calculations so that we can derive the work and the tangential force applied on the pedals. Now, this distance right here is going to be x rev. So that's the amount of distance traveled in one revolution. So now let's go back and get to it. We know that the work done on the pedals is going to be equal to the tangential force applied on the pedals over the entire circumference, right? And we know that the formula for circumference is 2 pi r. And we know that the potential energy, or the change in potential energy during that one revolution, is going to be equal to the same formula, mass times the acceleration due to gravity, multiplied by h prime minus h1. But in this case, and as in the case before, we're just going to assume that h1 is 0, is our baseline, because we're calculating from h1 to h prime anyway, right? So we could call this, h1 or h prime minus h1, or just h prime. It doesn't really make a difference. But we know that this right here is going to be equal to, right, x, the distance traveled in one revolution, multiplied by sine theta. That's just from the triangle. If we want to calculate this value right there, we need to multiply the x rev by sine theta. And the reason I'm doing this is because we know x rev, but we don't directly know h prime, so we need to calculate that. So if we were to go ahead and rewrite this, this is m times g times x rev times sine theta. Now, let me go ahead and rewrite these equations. So if this is equation 1, this is equation 2, and this is equation 3, let's go ahead and combine the equations, and what we end up with is that f tan multiplied by 2 pi r is equal to mg x rev sine theta, right? X sub rev being the distance traveled in one revolution. Now, what we're solving for is this value right here, and we really know all of the other values. The only value that we kind of don't know is r, but r is actually going to just be 1/2 of the diameter of the circle that the pedals travel in, which we were given earlier on, right? So we know what the diameter is. We can easily solve for the radius. So I'm going to rewrite this as f tan is equal to mg x rev sine theta divided by 2 pi r. So let's go ahead and make that r a little bit clearer. Let's go ahead and plug in the values that we know. I'm going to write them down again just because they're up there. We know that the mass is 75 kilograms. We know x rev is equal to 5.1 meters. We know theta is equal to 7.5 degrees. We know the acceleration due to gravity is equal to 9.8 meters per second squared. We know radius is equal to the diameter over 2, which is equal to 0.36 over 2, which is equal to 0.18 meters, right? So if we plug all of that in to our equation, what we end up getting is that f tan is equal to 432 0.616 newtons. Now, if we were to round for significant figures, what we get is that F, the tangential force, is equal to 433 newtons. And I'm going to go ahead and box that off, right? So, that should be all. That's parts A and B solved. Alrighty.